Introduction. I'm Martin Slepicka from the Technical University of Munich. I'm a research assistant at the chair of computational modeling and simulation. And I like to introduce our study on additive manufacturing. I guess everybody knows. It's a method is to use continuous process, so it's faster. And we have a very high modeling complexity. And due to the to introduce the term developed this framework. It's called Fabrication Information. And add a lot of other information that is necessary for the a fabrication model. And what you can see here is actually decided on using the IFC data structure. And we also implemented a directly use the FIM model for the printing process. You can see here a small scale clay print that's using this data structure. We are also focusing mostly on the layer pressing deposition strategy. And you apply it perpendicular to the print path. In the end, your result is like this. I'm there to supervise the whole process, and by myself, I can manage it quite easily. But on the construction side, as you see here, the same example, you have a lot of workers that have to also monitor and aid in the process. And if you look more closely, you have here on the left with the white helmet, a construction worker inserting some extra support material, and on the right, the guy is measuring if the print paths are actually accurately positioned. So he uses a measuring stick in this example, and yeah, so there's not much accuracy needed exactly, but we want to improve on that later. So question is, why are they doing that? Because of the material, it is still soft in the state when it's extruded. It's possible that some failures may occur. We can have plastic collapse or elastic buckling, or we have other issues, which are also not super easy to realize right away. But for example, the extruded material, as it is still soft when it is extruded out of the nozzle. And if that, if you stack up that, this effect over the layers, the distance of the nozzle that you have planned to the actually increasing, and then you have, in the extreme case, an effect that is showcased in this image, this coiling effect. So we don't want that. Other issues is, for example, tearing, if there's clogging, or if the extrusion rate was. Yeah, so how can we detect this? This is actually the core of the research. We want to monitoring. And in our study, we focused on a laser profiling. Then there's a question when you do it and how to. When, yeah, we can do it online. We can follow the printer with the profiler. We can do it layer-wise, so we can print one layer, scan it, then print the next layer. And we can also do quality inspection after the component is finished. Left side, you see a laser profiler, and it's emitting a laser line, which is captured by a camera. And you can very accurately measure the distance of the scanner. If you collect a lot of laser lines, you can combine it together to a surface model, as is visualized here. And the question is now how to control this laser scanner. As we use single laser lines and we need to combine it to a model, we need the position of the laser scanner at every time it measures. So we need a control mechanism where we know the position. The scanner is attached to a robot. We need to know the robot position. So for that, I've introduced this last year in ISARC 2023. We developed a control utilizes the film data structure and can directly control the robot and extruder. But we also can use this control mechanism to control other utilities. See also something that I showcased last year. We can control utilities that, for example, track the path of the case that you see here. There was a camera attached, which could then identify the filament. But how do we apply it for laser profiling? For that, I show you a little bit how the data structure looks like. So the IFC data schema. This looks a little bit complicated. Containing the boundary representation of the component. And we have the fabrication data, which is dividing that component into some discrete layers and contains the print path. And also other manufacturing data. So actually do scan planning, we can utilize this data and we can create paths follow or that are on an offset to these geometries. So for example, if we do a layer-wise scanning, we can use the layer surface and plan a path that is at an offset to the surface and moves along the whole surface. And if we do that, we have the distance, depth information of the scanner directly to derive any deviation as planned or as designed a surface. And we can see that as a deviation map or a heat map color code. So how do we feed back the information? As I said, we create a deviation map, and we can link that to our data structure as a texture to the respective surface. And we can link the data if we do layer-wise quality control, or if we do a quality control at the end to the boundary representation. So we did an experiment in our small-scale lab, and this is basically what it looks like. We scan of the layer, we transformed it into a heat map, and we also did a deviation map on the shape. So in the XY plane. And that is then fed back as a texture. All right, this is the lab that we used. We have on the right side the printer setup. Laser profiler. And yeah, that was the experiment. And to conclude the presentation, I would like also to give a small outlook why we need that and utilizing that in the future. We basically want to create this closed loop from digital to physical. By the first part you have seen, we can utilize our scan the data, go back. But now what we need to do is to interpret the data and to change anything that we have created later on. Time for questions now. So,